Hello guys, today we'll try to prove the inequality given as the pth norm of capital F is less than or equals to 1 over 1 minus 1 pth, the pth norm of small f, where big F is defined as this thing and x belongs to all real positive numbers and p is greater than 1, and we assume that f belongs to LP of 0 to infinity. Now in order to prove this, we'll start with a small baby step, and for that let's start the proof. We'll use one substitution as t is equal to sx on this capital F. So we'll get to know that this big F is nothing but 0 to 1 f of sx dx, right? ds, sorry. And here this is the right time to include the absolute value on this equality, and if we do so, we'll get this thing. And at this very step, what I will do, I'll take the pth power of this equality, so I will get this. Okay, and now what I'll do in the next step, I'll try to integrate this whole equality on all the positive 0 to infinity with respect to the dx measure. Okay, so what we'll get this thing 0 to infinity fx raised to the pth power with respect to the normal dx Lebesgue measure 0 to infinity absolute 0 to 1 f of sx ds whole p dx. Okay, right? So we have this thing. Okay, now what I'll do, I'll try to take the pth root at this very step. Okay, and then after that I'll try to recapitulate whatever I did till that very step. Okay, so what I'm going to do, I'm going to take the pth root. Okay, so let's start one more time and let's recall what we did. We were given the capital F was defined in this manner for all x being the real number, the real positive number, and p being greater than 1. And this is a small story that why p is greater than 1 here. I'll try to give the reason for that why we are considering p being greater than 1, and we are assuming that f belongs to the LP 0 to infinity. Okay, so we'll use one substitution which was given as t is equal to sx. So with the help of this substitution, we can get that the capital F can be defined in this manner on 0 to 1. Okay, so this is the beauty of this small substitution, and with the help of this substitution we can get fx is equal to 0 to 1 f of sx dx ds. And then what we did, we just did nothing, we took the absolute value and raised to the pth power. Okay, at this step. So this was a step 1, and this step 1 was composed with all those tiny steps. Now after that, what we can do, we'll take this thing and we'll try to integrate over 0 to infinity with respect to the normal Lebesgue dx measure, and then we'll take the 1pth root of that equality. Now at this very important step, we'll use the famous Minkowski inequality for integrals. Okay, so by the way, as you can see that the left hand side of this equality is nothing but the pth norm of capital F, right? Okay, and the pth norm of capital F is nothing but this thing. Okay, we have just discovered this thing. Now we'll try to apply the Minkowski inequality for integrals on the right hand side of this equality, and so that we can get this thing. The Minkowski inequality for integrals it's in itself a beautiful inequality. What it does actually, it just interchanges the first it actually it do a lot of things. Primarily, we'll focus only on two things for Minkowski inequality. First, it changes the domain of the integral, and second, it changes the Lebesgue measure. So since, as I said, so what will happen here, the domain will get changed. Okay, will get interchanged actually. So this 0 to 1 will come outside. Okay, I'm writing in this manner, it doesn't actually make a big difference. And then after that, you'll see that the Minkowski inequality for integrals is acted upon here. So this is the big square bracket. This is 0 to infinity. As I said, that the domain for the integration of the function gets interchanged. Now you see this absolute value will come inside to the capital F, and this will raise to the pth power. This absolute value will come inside, and this p will come to the function, to the f. And here, as I said earlier, that the Lebesgue measure will get changed, so dx will come inside, and this one pth which was present on outside of the whole big bracket over here at this step, at the last step, this one pth will come inside, and here, as I said again, the Lebesgue measure will get interchanged. So here dx comes and here ds comes. Earlier in the previous step, dx was outside and ds was inside. Okay, so you can see, let me change and let me show it to you by different pen. So this ds was inside, now here it is present outside, and this dx which was present outside, this has appeared inside. Okay, so this is a very important step for Minkowski inequality for integrals. And now again, this is Sx, right? But Sx is nothing but t, if you remember, right? So I'm continuing from here. So here the integral is from 0 to 1, right? And inside you have nothing but 0 to infinity f of t raised to the pth power, but absolute value is taken of f, and then here dt over s 1 pth, and this is ds. Right, now I'm going step by step. So you can see here the next step which corresponds here is nothing but 0 to 1, right? This is 0 to infinity f of t p dt. S is independent of the integration with respect to the t, so it will come outside, but don't forget that this s will have the 1 pth power. Okay, right? So what is this thing? What is this thing? This is nothing but the norm of small p, the small f, right? So you have nothing but it's 0 to 1 ds over s to the 1 pth multiplied by constant. Okay, because it's given that f was present in the LP space of 0 to infinity, so this is nothing but this thing. And if you do the integration of this thing, of this whole thing, you'll get 1 over 1 minus p multiplied by this name. And hence, finally, we have the capital F pth norm is less than 1 over 1 minus 1 over p multiplied by small p. Okay. Now, what this is called? This is called as Hardy's inequality. So this inequality is called as Hardy inequality. Let me write down over here. Okay, so in the starting I said that p has to be greater than 1. It's an important thing actually. The foremost reason that why we want p should be greater than 1 is this, that Minkowski inequality will fail if p is less than 1. Okay, so if you see uh, uh, a normal LP spaces, okay, in normal LP spaces the triangle inequality gets failed if p is less than 1 but greater than 0. And we'll talk definitely something related to that in my next video, so that you guys can have a clear picture that why Minkowski inequality gets failed whenever the p is smaller than 1 but greater than 0. So this is very important, that for normal Lebesgue measure space LP spaces, the p that we are considering, it should be greater than 1, so that the triangle inequality is satisfied. And that is very important, for the norm spaces. This is called as norm spaces, right? So the norm of f plus g should be less than the individual norm of f and g. So that inequality is called as Minkowski inequality for normal non-linear spaces. And here this we use Minkowski inequality for integrals. Okay, so once again we studied about Hardy's inequality, and which says that the norm of capital F is less than 1 over 1 minus 1 p multiplied by norm of small f, where f is defined in this manner. Okay, it has lot of use in industry. I don't remember it now, but obviously one can find it on the internet. Okay, let me give you the whole proof in this manner so that you can have a look. So okay, see you, bye. And by the way, please subscribe my channel if you find it interesting. A lot of new things, especially related to graduate studies of mathematics, will come up on this channel. Okay, bye, have a great day, peace.